Good evening and welcome to tonight's Triple Chemistry C3 Part 2 Revision Hangout. The session will start in just 1 minute time. If you grab some paper, a pen and a calculator, that's what you'll need this evening. If you're from Nodewood, please put your name on the frog page and that's where you can ask any questions you've got throughout the evening. So again, if you grab a calculator, you'll need that for some of the calculations that I ask you as we go throughout. And also remember, this is available on Catch Up as well. Okay, good evening all and welcome to this Triple Chemistry Revision Hangout. Thanks for those of you who've put your name on frog. I hope this is useful for you. It covers the second half of the C3 topic, and if you grab that pen, a paper and calculator, you'll need those for the session. So let's get started then. First of all, just want to give you a summary of what I want to cover today. We're going to talk about energy and fuels, hydrogen fuel, energy diagram, and bond energy, so loads of stuff about energy to cover. And also we're going to do some titration calculations, have a look at alcohols, carboxylic acids and esters, and right at the end you've got to keep your energy for the end because that's when we look at those horrible tests for metal ions and non-metal ions. So first of all then, let's talk about energy and fuels. Now this kind of equation they will probably give you in the exam because you don't have an equation sheet for physics, so every single question I've seen in relation to this, they've actually given you that equation, sorry. But if you can't remember it, think about back to physics. It's exactly the same as that specific heat capacity equation you'll see in P1, which is written as E equals M times C times theta. It's exactly the same as that. It just says that energy is mass multiplied by specific heat capacity multiplied by a temperature change. So in chemistry, the way we use it is in something called calorimetry. And that is when you can test the energy released. We tend to talk about energy released in chemistry rather than energy transferred because we're looking at the energy released by perhaps fuels or food. So you'd have a similar setup to this. For example, here might be the fuel that you're using, or it could be a piece of food, and you would heat some water, a fixed amount of water. And you would want to calculate the energy that's transferred by that fuel to the water. A lot of questions around this relate to how you would set up the equipment. So you need to think about the fact that you would probably want some sort of insulation around your equipment to make your result as accurate as possible, because what you don't want is you don't want energy being lost out of the sides by radiation or out of the sides of the beaker either. You want all the energy being transferred into the water. They also might lead you to suggest that it would be good to have a lid on top as well, to prevent any heat loss by evaporation out of the top. Okay, so you want to put a lid on it, and then you'd have some kind of thermometer in here to have a look at the temperature change. So what they tend to give you is the specific heat capacity of water. You might have seen that as 4,200 as well. That's in joules per kilogram degrees Kelvin. This one is in joules per gram degrees Celsius, sorry, and 4,200 you would see that as joules per kilogram degrees Celsius. So you might see it either way, but they'll give you that value and then you need to have a look at the question to work out the energy change. So you can use this to work out calories, for example, how many calories are in food. And in an exam, if they do talk about calories, they will give you the conversion to joules. Okay, so don't worry about learning what a calorie is. They will give you that conversion. But just bear in mind, you will need to know that this process is called calorimetry. Okay, without further ado, here's a question for you to have a go at. If you just highlight the key information in the question, you should be able to use this equation to work it out. So just have a go. I'll give you a couple of minutes and then we'll come back. Just had a question about whether you have to work out the grams into kilograms. You might have to convert it if they give you a mass, for example, in kilograms, whereas they've given you that in grams, in joules per gram degree C. So just look out for that. They will tell you that this is joules per gram degree C, and you just need to make sure then that your mass is in grams. If they give you this in joules per kilogram degree C, then you will need your mass in kilograms. So really good question, just bear that in mind. So all you need to remember is that you need to keep the mass in the same units as what you will see inside that specific heat capacity unit. Okay, so this is where a highlighter in the exam comes in important. So you'd highlight the key bits. It says finds the energy released when a biscuit is burned. Use his results to calculate the energy released by the biscuit. So Tom put 500 grams of water in a beaker. He set the biscuit alight and held it under the beaker, and the water temperature increased. So we've been told to work out Q, the energy released. We've been given a mass, and we've been given a temperature change. That delta just means change. So we simply need to just put that into our equation. Q equals M for mass, which is 500, multiplied by 4.2, multiplied by 27, which would give you 56,000, if my mass is correct, 700 joules of energy released. Okay, so very well done if you've got that one correct. It's just a simple application of the equation, and just bear in mind the good practice when you're trying to calculate the energy released by the fuel. So moving on then, we're going to talk specifically for a little bit about hydrogen fuel. So there's not a massive amount of talk about hydrogen fuel in the C3 bit, but there's no reason why they couldn't give you a 6 marker on it. There's absolutely no reason. So hydrogen fuel itself, just like any other fuel, undergoes a combustion reaction, reacting with oxygen and producing water, H2O. Now, the good thing about this reaction, comparing with perhaps a fossil fuel like methane, methane in combustion would produce carbon dioxide and water, okay? But it's not balanced, but just bear that in mind. So on the other hand, though, hydrogen does not produce CO2. So that's really important. It's not producing CO2 when it's burned, and therefore it's not contributing to global warming. So it's a really big benefit of that hydrogen fuel. And we're trying to develop these hydrogen fuel cars at the moment, so that we've got a situation where we've got a car producing only water and not carbon dioxide. So that's the main positive, that no CO2 is produced, only water. Now, there's a few negatives to using hydrogen as a fuel. One of those is that it's expensive to produce an engine that only uses hydrogen. So redesigning that engine and making it safe for the hydrogen fuel. Because another negative for hydrogen is that it's really hard to store because it is very flammable. So yes, it's a great fuel because it's flammable, but it also has its difficulties in actual storing it. Also, because it's a gas, it takes up loads of space. So compared to diesel and other fuels that we can store as liquid, it takes up loads of space because it's a gas. And also, when we make hydrogen, either we can split water to make it, or we can get it from perhaps a fossil fuel. If you're splitting water, you're talking about loads of energy needed to actually make that hydrogen fuel in the first place. And if you're talking about getting it from fossil fuels, you've obviously still got that problem that you're using a non-renewable source to make that. Now, where this hydrogen fuel technology is going is in the use of a fuel cell. Now, you don't need to know much about how fuel cells work or the reactions that go on inside them, but you just need to know that a fuel cell is something that can take a fuel and generate electricity from it. So, for example, we've got hydrogen and oxygen reacting in a fuel cell, and it then allows the heat from that reaction, which is going to be exothermic because it's a combustion reaction, to transfer into electrical energy. So it's the idea then that we're providing a circuit with some fuel. The heat that's generated from that reaction is transferred into electrical energy. And this technology was developed a while ago, but they're starting to try and use fuel cells in cars, for example, to obviously reduce this problem here with CO2 being released. So that's a little bit about hydrogen. Bear in mind that they might ask you a 6-mark question on that one. They might ask you for advantages of hydrogen fuel and disadvantages compared to other conventional fuels, and leading into this idea of the fuel cell. Okay, still on the topic of energy, we're going to move on to energy diagrams. These are really common in the exam, and you just need to read what's going on in the diagram. So use your highlighter or pen. You're thinking about reactants and products. Remembering in an equation, you've got reactants on the left turning into products. So in this reaction, we look at the side, it says energy here. So we can simply write down that the energy of the reactants is lower than, or less than, the energy of products. So in that case, because the energy of the reactants is less than the energy of the products, then energy must have gone into the reaction, because these products at the end have got more energy. So energy must have gone in, therefore it is an endothermic reaction. On the other hand, over here, we've got reactants and products. And this time, the energy of the reactants is greater than the energy of the product. So the energy must have been lost. So this is an exothermic reaction, which has given out energy to the surroundings. So there tend to be 2-mark questions in relation to this. So how do you know, for example, that this is an exothermic reaction? And they want the idea of the energy of the reactants is greater than energy of the products. Don't make it any more complicated than that. The other thing that we need to be able to do is label the activation energy. So that's from the reactants to the top of the graph. That's the energy needed for the reaction to happen. And again over here for the exothermic diagram. And finally, what you'll need to do is put in the pathway for a catalyst. So this here shows an alternative pathway for the reaction. And this has a lower activation energy. When you're talking in C2, you tend to be talking C1, you tend to be talking about catalysts being things that speed up the reaction without being used up. In C2 and C3, you need to be talking about catalysts in terms of what they're doing. They're providing an alternative pathway for the reaction with a lower activation energy. If they asked you what a catalyst did or how it worked, that would be your 2 marks there. The other thing I want to bear in mind is this delta H over here. This delta H is the change in energy. So for an endothermic reaction, that is positive because you're gaining energy. So you might have a value, for example, of plus 180 joules. That change in energy, that delta H. Over here, the energy change in the reaction would be negative. So perhaps negative 180 joules, for example. And that tells you that that's an exothermic reaction. So that delta H means change in energy. Okay, so that's it on energy diagrams. I've got a few questions for you to answer. Please post any more that you got on Frog, and I'll answer them as we go. So I'll give you a couple of minutes and then come back and see how you got on. Okay, so let's see how you got on with these questions. It says, number one, does this graph show an endothermic or exothermic reaction? Well, if you have a look over here, the energy of the reactants is greater than the energy of the products. So the reaction must have lost energy. So it must be an exothermic reaction. And here we want the idea that the energy of the reactants is greater than the energy of the products. Question 3, copy the graph and draw an arrow to show the activation energy. Well, that needs to be here. I'll just give that a label A. And it says add a line to show the effect of the catalyst. So that would be from here and a dotted line to show that lower activation energy pathway. So very well done if you got those correct. We're going to stay with the theme on energy and we're going to look at bond energies now. So with bond energy questions, they will give you everything that you need in the equation, but there's something really important that we need to remember, and that is this box over here. It is the idea that energy is released when bonds are made. Energy is taken in when bonds are broken. Now, this one is quite easy to remember because you can think about a molecule being bonded together, and you can think about the idea that to break that up, you're going to need to provide energy to perhaps get those bonds moving and shaking and wiggling up. This concept is slightly more difficult, the idea that energy is actually released when bonds are made. But when you do these bonded energy questions, if you remember these facts, write them down in the white space. They'll be so important for you to remember. So this is the type of question that you will get asked. It said, is this reaction exothermic or endothermic? If you remember, this is the Haber process reaction. It's actually reversible, and we'll talk about that in just a sec. The first thing you'll have to do is balance the equation. That's number one. And then they will tend to give you the structure of the molecules involved. So here it tells you that N2 is actually N triple bonded to N, H2 is HH, and ammonia is NH3. They will also give you then a table that looks a little bit like this, which shows the bond and the energies involved. So what I'd like you to do is have a look at this question. I'd like you to balance it first of all, and then use this information and the bond energies over here to try and answer this question, please. Is the reaction exothermic or endothermic? So I'll give you a couple of minutes as it's revision. Hopefully you'll remember doing these type of things. And then I'll come back and I'll see if you've got it correct. So again, feel free to post any questions you've got on Frog. We're just having a go at this question, and then I'll come back in just a sec to see if you got it right. Remember to balance the equation first before you do the rest of the calculation. Okay, just one more minute and then we'll come back and we'll go through the answer and hopefully you would have got it correct. Okay, so let's go through the answer then. If you haven't finished just yet, feel free to pause and then play again. So for this question, it says, is the reaction exo or endothermic? First of all, you need to balance the equation. So because there's 2N there, we need to put a big 2 over here. But that then makes 6 hydrogen, so we need to put a 3 here. So having a look at the bond energies on this side of the reaction first of all, we've got N2, which is simply an N triple bond N, so that's 944. And we need to add that to 3 lots of H2. So that's what H2 looks like. So we need 3 lots of those. So we need to add that to 3 lots of 436. And that will give us a total bond energies on this side of 2,252. On the other side of the equation then, we've got 2 molecules of NH3. And this molecule has 3 NH bonds. It's got 1 there, 1 there, and 1 there. So we actually need 2 lots of 3 lots of NH bonds. So we need 6 NH bonds altogether because there's 3 per molecule and this number tells we need 2 molecules. So that will give us on this side 6 times 386, and I've got that 386 from over here, and that's 2316. So you can see that from the reaction we've gone from a situation where we've had 2,252 to 2316. Now this is the crucial bit, and you need to remember that energy is released when bonds are made, energy is taken in when bonds are broken. So down here, this is the energy needed to break bonds. So that means that the energy has gone in. Whereas on the other side, this is the energy released when bonds are made, and therefore that's energy out. And if you write those key bits under your numbers, that will help you out a lot. So we know that that is an exothermic reaction. And actually, if you take 2316 away from 2252, 2316 minus 2252, you will then have a negative energy change, which from our graphs before will tell us that negative energy change is an exothermic reaction. So you might have done that extra step as well to do 2316 minus 2252. I'll just do that on my calculator now. 2316 minus 2252, which will give you an energy change of 64. Okay, so, and that will be in the kilojoules per mole from those units up here. Okay, so that's how you look at bond energies. They'll give you a table. You need to remember these things though. Balance the equation and remember the information in this box. That's super important. Okay, we're going to move on now to alcohols, carboxylic acids and esters and how these all link in together. So we're going to start off with alcohols and then we're going to move on to carboxylic acids and then finally we're going to end up with esters. So from C1, I'm hoping that you'll recognise these prefixes, the beginnings of words, meth, eth, and prop. And we'll need to remember these throughout the alcohols and the carboxylic acids. So meth is anything with 1 carbon, eth, 2 carbons, and prop, 3 carbons. So we've got 3 different alcohols that we're going to talk about for your C3 exam, and they all sound very similar. It's methanol, ethanol, and propanol. And we'll need to know how to draw them and also how to write their formulas as well. So let's start off with methanol. You need to remember, in all of these 3, they'll have the same functional group, and that is OH. That's the functional group for an alcohol. That means every single alcohol has this ending on the molecule. So for methanol, what I would recommend is start with a functional group and find out how many carbons it's got. It's just got 1. Okay, and then fill it up with hydrogens. Remembering every carbon has 4 bonds, so this would be our molecule of methanol. Again, for ethanol, start with a functional group, add your carbons on, so we've got 2 for ethanol, and then fill it up with hydrogens, making sure we've got 4 bonds for every carbon. And finally, propanol, start with functional group, add your carbons on, 1, 2, 3, and then do it that way, filling up with the hydrogens. Some people like to draw propane first and then scrub out the last H and put an OH on the end. That's absolutely fine as well. That's good to do. And then we need to name them. So this is our structural formula, okay, where we might be asked to draw them, and you could be asked to draw any one of these 3. And then we might be asked to name them as well. So what we do is we have to name the methanol so that the functional group is showing, so that we know it's an alcohol. So we write it as CH3OH, showing that functional group on the end. So this is the chemical formula. For ethanol, it would be C2H5OH. So that OH has always got to be on the end. And for propanol, C3H7OH. So make sure that you're always leaving that functional group just on the end there. Because these are very similar in structure and they only change by 1 small thing, so each one just adds each time just that CH2, and they all have the same structure, we call these a homologous series. So it's just 1 S, homologous series. Okay, where homo is like the same, so these are all very similar molecules, they just differ by 1 small thing. Now, alcohols are really important as solvents and as fuels. Don't forget, as fuels, you've got things like ethanol, which is used as a biofuel in cars. You would have seen that in C1 as well. And also as solvents, if you try and wash things off with water and water is just not cutting it, then you can use an alcohol cleaner, which acts as a solvent, so it dissolves all the dirt, and it can be used as a really good cleaner. So solvents are just things that dissolve solutes or dissolve solid things, so they can make good cleaning products and things as well. So if they ask you 2 uses of alcohols, you need to get the words solvents and fuels down. So just like other fuels, they burn in air to produce carbon dioxide and water. So obviously they're reacting with the oxygen in air to produce CO2, obviously leading to global warming. They could ask you, they could link a little bit more of a C1 question. They could link ethanol and fuels to hydrogen and fuels and ask you to compare those. Number 2, dissolve in water to produce a neutral solution. And that will come important in a minute when we compare to carboxylic acids. But if you dissolve an ethanol in water, the solution is neutral. And secondly, we've got another reaction that we need to remember for the alcohols, and that is that they react with sodium to produce hydrogen. And I'll just show you a reaction now that you might see with that. So I'll just clear the screen and I'll just show you an example of one that you might see. If you have ethanol react it with sodium, you would produce something called sodium ethoxide plus hydrogen. Now, in your exam, I'd be very surprised if they asked you for this, but I would expect you to be able to complete this equation, ethanol plus sodium, knowing that it's hydrogen that is produced at the end. So just remember that when they react with sodium, hydrogen is produced. Okay, moving on then, we're going to go from the alcohols to the carboxylic acids. And to get there, we add oxygen. So we oxidize the alcohol. So if we use ethanol for an example, we'd react ethanol with oxygen to make a carboxylic acid. In this case, this would be ethanoic acid plus water. So we oxidize the alcohol, adding oxygen to make our carboxylic acid. And there's a couple of ways that we can oxidize them. We can add a chemical oxidizing agent. So that's by adding a chemical, which is going to provide us with that oxygen in the reaction. Or we could use microbial action, whereby microbes will react and microbes will provide the oxygen through fermentation. Okay, so this is kind of a fermentation reaction. So there's two ways you can do it, either by adding a chemical, or microbes in the air perhaps can get into the ethanol and produce this carboxylic acid. Now, this is exactly what happens if you leave wine open, for example. If you leave wine open to the air, leave the bottle off, then ethanol is the main constituent of alcohol. That's something that you need to know for your exam. So ethanol in the wine, if oxygen can get into it and microbes from the air, then that ethanol can turn into ethanoic acid. And this is what's in vinegar. So that is why wine will go off and taste like vinegar, because of the oxygen from the air getting in and turning it into this ethanoic acid, which tastes like vinegar. So again, these prefixes we need to know, meth, eth, and prop for the carboxylic acids, and we call them methanoic acid, ethanoic acid, and propanoic acid. And these don't be put off by this name, carboxylic acids. It's a really difficult name, but these are the things that we really need to remember: methanoic, ethanoic, and propanoic. So again, meth has 1 carbon, eth has 2 carbons, and prop has 3 carbons. Now, like before, we said for the alcohols that had a functional group OH, the carboxylic acids have a functional group COOH. So let's try and draw the structural formula for these. And we start off with our carbons, and we can then draw the groups ending on. So we got OH, so it's COOH. Remember the double bond to the O. And then because this carbon has already got 3 bonds already, it can only have 1 more to make 4. Ethanoic acid, we use this C at the end to make the COOH. And, this should be OH, sorry, COOH. And then we add the hydrogens in around. Oops. So this one here already has 1, 2, 3. I'll draw that one again. Always be careful when you're drawing the correct number of bonds on these, because you make silly mistakes like me. So you've got COOH as your functional group, then you've got another carbon, and you need to add the bond. So this one has already got 1, 2, 3, 4 bonds, so we can only add the hydrogens to this one over here. Finally, propanoic acid, you've got the COOH on the end, 1, 2, 3, 4 bonds made, so we just add our hydrogens in there and in there. And how we write these then, again, we want to show off that functional group at the end so that we know it's a carboxylic acid, and then we just write everything to the left-hand side. So if I were to put a line in here to show you, we've written the COOH bit. So we do that for each one. So I'll just do that for each one. And then we have to write the bit that's in front of it. So this one is slightly funny. It will just be called HCOOH, and that is where we've got the H from there. This next one down, you can see we've got CH3 and then our COOH. So we've got CH3, COOH from this bit here. And this one over here, there's a couple of ways you can write it, but the way they like to write it in your spec is this bit and then this bit. So they like CH3, CH2, COOH, and I'll just highlight that to show you where I've got those from. The CH3 comes from this part of the molecule here. CH2 comes from this part of the molecule here, and then the functional group on the end, COOH. And again for these ones over here, COOH from this part, and then the CH3 from here. So what I recommend you do is draw the structural formula starting from the COOH bit, and when you write the formula here, start with the functional group and then just maybe even draw yourself a dotted line and see whatever is on the left hand side. Okay, this bit here is a really important bit for hire because it's really common for them to put in because they've made it very specifically for the higher tier. And this is the idea that carboxylic acids dissolve in water to produce an acidic solution, and that's opposite to that alcohols, and the alcohols made a neutral solution, if you remember, but they dissolve to produce acidic solution, but this is going to be slightly different from our normal acid because they give away hydrogen ions to make an acid. So remember, an acid is full of those hydrogen ions. But these carboxylic acids don't completely ionize. That means they don't give away so many hydrogen ions. So not many hydrogen ions are released. And what this means is these acids are weaker than other types of acids with the same concentration. So these acids here would have a higher pH than other acids with the same concentration. And what that means then is, if I write it up here, if you've got something like 0.1 molar concentration hydrochloric acid, and if you had 0.1 molar, the same concentration of methanoic acid, HCOOH, this one would be a stronger acid and this one would be a weaker acid, because this one would have many more of these hydrogen ions free to move around, whereas this doesn't completely ionize. There's not many hydrogens released. So this one may, for example, have a pH of 3, just for argument's sake, and this one would have a higher pH of perhaps 5. So this is really important because they really like to ask this question a lot. Finally then, the carboxylic acids react with carbonates to produce carbon dioxide. So basically they're saying that just like any other acid, they will react with carbonates and produce that carbon dioxide. If you ever see that word carbonate, circle the word carbon and think to yourself straight away, carbon dioxide. So the only thing I want you to take away from this is the fact that the salts are slightly different. If you remember from salts, from sulfuric acid making sulfates, nitric acid making nitrates, chloric acid making chlorides, for example, the salts are written slightly different for carboxylic acids. For example, you've got ethanoic acid plus calcium carbonate making calcium ethanoate plus carbon dioxide plus water. Or you could have example methanoic acid plus calcium carbonate making methanoic acid, calcium methanoate plus carbon dioxide plus water. So bear in mind these salts end in that OH, and they might be a methanoate salt or maybe a propanoate salt to recognise. Okay, moving on then, we're going to go from carboxylic acids and alcohols to something called esters. And to get there, you react an alcohol with a carboxylic acid and you get yourself an ester plus water. Now the functional group for an ester you will see as COOO, but you will see that in the middle of the molecule, so not at the end of the molecule, but you'll see it at the end, and I'll show you exactly where in just a sec. Now there's only one ester that you need to recognise for your exam by name, and that is ethyl ethanoate. And I'll show you how you get to that ester now. So remember, an ester is an alcohol plus a carboxylic acid. That's how we make the ester. So to make ethyl ethanoate, we would have ethanol added to ethanoic acid, and that will give us ethyl ethanoate plus water. Okay, so that's the one we need to recognise. You'd have to be able to complete this equation to remember that ethyl ethanoate. But you would also perhaps have to recognise an ester by seeing a molecule with this functional group in it, this COOO, as opposed to the COOH that you see in a carboxylic acid. And I'll just show you where you would get that from. So if I were to draw ethyl ethanoate, it would look something a bit like this. And this is where you get your functional group from here. So rather than the carboxylic acids, which had the COOH on the end, these have this functional group in the middle, this kind of COO, and that's how we recognise the esters. So it's not the same as having COOH on the end of the carboxylic acids. It's this COO in the middle. So what you'll have to do is recognise this as an ester. If they say what type of molecule is this, but the only one you'll have to name is ethyl ethanoate. Now, why are esters good? Well, they make really useful perfumes. They're really fruity and sweet smelling. And the reason why they make good perfumes or flavourings in food as well is that they're fruit and sweety. They're also quite volatile, so they turn into a gas easily, volatile, but that also makes them quite flammable. And this can be a bad thing. So if these are put obviously into an alcohol, if people abuse perfumes and things like this, it makes them quite dangerous because they can catch light quite easily. Some people are also worried that esters are toxic, so don't like the fact that they're used in perfumes and flavourings for food. And they also can irritate your nose and your throat. So a lot of people are worried about that in terms of their use in perfumes. So fruity, volatile. The reason why they're good in perfumes is because they mix well with alcohol. So perfumes are all often alcohol based, and these esters mix well with alcohol. Okay, they don't mix well with water. Okay, but they do mix well with alcohol, which makes them really useful for perfumes, but it also makes them, they're also volatile and flammable as well. Now, the only other thing I forgot to mention before when I talked about the equation for esters, I said that we had an alcohol plus a carboxylic acid to make our ester. We had water as well. What you also need to remember is at this point, a rather unusual catalyst is used, which is a concentrated acid, and often a concentrated sulfuric acid. So in this reaction, quite an unusual catalyst, but you might see this in your exam. So when making an ester, this concentrated sulfuric acid is used. So here are a few questions for you on alcohols, carboxylic acids and esters. I'll give you a couple of minutes for you to have a go at these, and then I'll come back and see if you got them correct. Okay, so just had a really good question about drawing the bonds in diagrams for carboxylic acids and alcohols and things like that. If you're going to make little mistakes like me as you're drawing them, then what I'd recommend is that you draw them in pencil first, or maybe draw them in the white space somewhere else. But then when you draw them for your real thing, I would recommend draw them in pen, because your exam papers will be copied and sent electronically to whoever's marking it. And therefore, if it's in pencil, you'd worry that those wouldn't be shown properly. So I would recommend drawing them in pen, but maybe draw it on the white space around first, just to make sure that you're going to get it correct. Okay, 1 more minute left. Feel free to post any more questions you have on frog, and then we've just got 2 more topics to cover. Okay, I'm just going to go through the answers now. If you've not quite finished, feel free to pause and then catch up. It says, when an alcohol dissolved in water, does it form a neutral or acidic solution? It forms a neutral one, because remember, carboxylic acids, the clues in the name, form the acidic solutions. What are the 2 ways in which oxygen can be provided to turn an alcohol into a carboxylic acid? Well, it could be a chemical oxidizing agent, or it could be microbial action, so using microbes and fermentation. Question 3, draw the structure of propanoic acid. So first of all, think to yourself, what is that? It says acid, so it must be a carboxylic acid. Functional group is COOH. Prop has 3 carbons because monkeys eat peanut butter. If you remember from C1, MEPB, monkeys eat peanut butter. So I know I've got to draw something with 3 carbons. And then I know the functional group is COOH. And then I just fill in my hydrogen. So 1, 2, 3, 4 bonds, so nothing else can go there. But here I can add 2, and here I can add 3. And that's your structure for propanoic acid. Write the chemical formula. That would be, if you looked at this part here, you've got CH3. This part here, CH2, and then COOH. Draw the structure of methanol. Well, methanol, remember that's the functional group is OH, and meth is 1 carbon. So we draw our 1 carbon, the functional group, and then we add our hydrogens on. And the chemical formula for methanol, well, you take this bit, that's your CH3, and then add your OH on, CH3OH. And give one use of an ester. You could have had something like perfume, or in flavourings, food flavourings, or something like that. So very well done if you got those correct. Got 2 more topics to go. We've got titration, and then we've got identifying positive and negative ions. So get your calculators ready for the titrations. Here is the setup for titrations. You will have a burette. You might get a 6-mark method question on this. Why not? A burette, a conical flask. And you might have some sort of acid in here, some sort of alkali in here, and you will be doing a neutralization reaction. So in here, you would also use an indicator, but you wouldn't use universal indicator because that shows a gradual change. And you don't want a gradual change. You want something called an end point when it's going to change suddenly and straight away. So the universal indicators that they use tend to be things like methyl orange or something called phenylphthalein. Okay, so these two indicators are more likely to be used in a titration than a universal indicator. Now, there's an equation we need to remember for a titration, and that is this one here, which is the number of moles divided by concentration multiplied by volume. Now, if you can't remember this one, try and remember it maybe pictorially. So I remember it in a really weird way. So welcome to my brain. Here we go. Here's a mole. Definitely looks like a mole. And he's on top of a car for C and a van. Okay, so it's a weird way to remember. If that helps you, then there you go. So we got mole, car and van. Okay, so you could write M here for mole if you want, or numbers of mole. So that's the kind of idea we want. I tend to use N for the numbers of moles, C for concentration, and V for volume. Okay, so moles over cars times van, or moles over a concentration multiplied by volume. So the one thing that we need to watch out for, the one red herring in this question, is the volume they normally give in centimeters cubed, but the concentration they give in moles per decimeter cubed. So when you get that centimeter cubed, what you need to do is divide by 1000. Okay, so centimeters cubed divided by 1000 will give us the volume in decimeters cubed. So let's go straight into some calculations then for titrations. I'll go through this one with you, and then I've got one for you to work out yourselves as well. So let's highlight the key information. Mikey carried out a titration to find the concentration of a solution of sulfuric acid. 35 centimeters cubed of sulfuric acid was neutralized by 55 centimeters cubed of 2 molar per decimeter cubed potassium hydroxide. This is the equation. Now, the first thing we need to do is check to see if is it balanced. And at the moment, it looks like they've done that bit for you, which is fantastic. Second thing I'd recommend you to do is any white space around this equation, write yourself a table of acid against alkali. And then for each one, you need to write down the information you've got in your table. So I'd write number of moles, concentration, volume. Number of moles, concentration, volume. So over here, we've got acid, and we've got a volume for acid, and we've got a volume for alkali, and a concentration for alkali. So we fill in our numbers over here. So we've got 35, but don't forget we have to divide that by 1000 because this is in centimeters cubed and we need it in decimeters cubed. So write that in your table like that. For the volume of alkali, we've got 55 divided by 1000. For our concentration, we've got nothing for our acid, but we've got a 2 molar alkali. So from there, we can remember to write down our equation, N equals C times V, or you can write it as the triangle if that helps you to remember it. And we have a look at our table and think, what bit of information can we work out? We can't work out anything for the acid yet because we've only got one number, but we can work out something for the alkali. So we can do, for the alkali, N equals C times V. So the number of moles equals 2 multiplied by 55 divided by 1000. And when we do that, we will get the number of moles as 0.11. And we can fill in our table over here, 0.11. Now, once we've got everything for the alkali, our next step is to use this balanced equation. The whole point you balance it is because you need it. You need to know the ratio of molecules of alkali to molecules of acid. So our ratio here is 2 to 1. So we write that down over our equation, 2 to 1, and then we write in the number of moles that we've got. So we've got 0.11, and because it's a 2-to-1 ratio, that means we must have 0.055 moles of sulfuric acid, because we've just had to halve it, because 2 halved is 1, so halve that and we end up with 0.055. And then we can fill in this bit of the equation, 0.055. So now we've got 2 bits, we can finally work out C. We can work out the concentration of acid needed to neutralise that potassium hydroxide. So we do rearrange our equation, C equals N divided by V, where C equals the number of moles divided by the volume, which was our 35 divided by 1,000. Oops. So that will give us a concentration then of 1.6 moles per decimeter cubed, which we can then fill in that last bit of information. So this is seriously how I'd recommend to do it in this table format like this. If you've got another way to work it out and that works for you, then that's absolutely fine, but try and get all the information down that you need. Now, the second thing that they might ask you to do is calculate the concentration of the sulfuric acid in grams per decimeters cubed. And if they ask you in grams per decimeter cubed, you need to be thinking about what moles are. And you will use your periodic table. So you need to think about the relative atomic mass of hydrogen, which is 1, the relative atomic mass of sulfur, which is 32, and the relative atomic mass of oxygen, which is 16. If they ask you in grams per decimeter cubed rather than moles, you need to multiply this answer by the relative formula mass of H2SO4. So H2SO4, we've got 2 for hydrogen, because it's 2 times 1, added to the 32 for sulfur, and added to the 4 times 16 for oxygen, and that will give you a relative formula mass of 98. So if you then multiply your 98 by 1.6, that will give you 156.8 grams per decimeters cubed. Okay, so bear in mind that next step, this kind of thing will be 4 or 5 marks for a titration calculation. So a couple of things to remember: balance the equation, write down all the information that you've got, and you need to remember this equation. So I've got a question for you to have a go at. So use your calculator and you're working out, have a go at this question, and then we'll come back and see if you got it correct. Feel free to ask any more questions on frog as well. We've got one more topic to do, which is the positive and negative ions and testing for those. So we should be done in about 10 minutes time. Okay, just to help, I'll just remind you that we need to check that it's balanced. And I'll write the relative atomic masses of nitrogen, which is 14, and hydrogen, which is 13. And I'll also remind you to draw that table of acid versus alkali. Okay, just one more minute then, and we'll see how you get on with those, and then we'll move on to our final topic. Okay, so I'm just going to go through this answer. I'm conscious we're tight for time, so if you want to go through this fully yourself, feel free to pause and catch us up. So we've got 40 centimetres cubed of ammonia. and it's neutralized by 20 centimeters cubed of 2 molar concentrated nitric acid. So we've got some information on volume for our alkali, volume for our acid, and concentration for our acid. So we put these values in. We've got a concentration of acid of 2 and a volume, again, centimeters cubed. So we need 22 divided by 1,000 to turn it into decimeters cubed. For ammonia, we've got 40 divided by 1,000, and that's all the information we got. So the only bit we can work out now is this N. And if we remember, N equals C times V, so the number of moles equals concentration times volume. So we can work out this bit, and we will end up with 0.044. And that was just by doing 2 multiplied by 22 divided by 1,000. And that will give us our 0.044. Now then we look to see if the equation is balanced. So we've got 1N, 2N, and over here we've got 2. We've got 3, 4 hydrogen. Over here we've got 4, and we've got 3 oxygen. So it's already balanced, which is great. And then we look at the ratio. So we've got 1 molecule of ammonia to 1 molecule of nitric acid. So we have a look over here. We've got, in our question, we've got 0.044 moles of nitric acid. So because it's a ratio of 1 to 1, we must also have 0.044 moles of ammonia. So we can fill in this part of the table, 0.044, and then we need to work out our C. So rearrange this equation, you get C equals N divided by V, whereby C equals 0.044 divided by 40 divided by 1,000. And that will give us a concentration of 1.1 moles per decimeter cubed. Then the equation asks us for the concentration in grams per decimeter cubed. So we need to multiply by the relative formula mass of ammonia, which is NH3. The relative formula mass of ammonia is 17, which is 14 plus 3. So then we have 1.1 multiplied by 17, which gives us the concentration in grams of grams per decimeter cubed of 18.7 grams per decimeter cubed. So those are the titration calculations. I'd recommend going over those again. Feel free to ask your tutor for, oh, sorry. You can see I've worked out right down here. I've just told you over here that hydrogen is 13. Obviously it's 1, but then I wrote my 3 next to it because I had 3. So sorry about that. The relative atomic mass of hydrogen is obviously 1, which I've calculated down here, but 14 for your nitrogen added to 3 lots of 1. But I got a bit carried away up here. Okay, so sorry about that, but hopefully that makes sense for you. So the relative formula mass of ammonia is 17, and then we multiply that by our concentration to get grams per decimeter cubed. So moving on to the final thing then, we are going to look at identifying substances. So we're going to look at substances that are ionically bonded, so a metal and a non-metal. And we are looking at things like magnesium sulfate, for example. We might look at calcium carbonate. We might look at potassium iodide and all things like this. And essentially what you're going to do to identify that substance, if you just had a random powder that you wanted to identify, there's a few tests that you can do. And you are looking at essentially splitting that molecule up and splitting that compound up and looking at the positive ion and looking at the negative ion, or thinking about it, looking at the metal ion and then looking at the non-metal ion, remembering that all metals make positive ions and all non-metals make negative ions. So this is what we're going to do in the next couple of slides. We're going to identify the metal part and then the non-metal part, and it will tell us, therefore, for certain, for example, that this sample is either calcium carbonate or potassium iodide or magnesium sulfate, for example. So first of all, then we're going to look at flame tests. Now, there's no real easy way to work out flame tests. Okay, there's one that might help you remember. It kind of just groups the metal with the colour, but they're not always in the right order. Okay, there's not many good ones online to help you remember. Britain's got really clever students overthinking the learning of pretty coloured lights. If you've got some way to remember them, some people remember a few of them, like bogies are green, okay, and things like that. If you've got a few ways to remember them, put them on a post-it note in your room and learn them. You can always brain dump them and write them straight away on the front of, on the inside of your paper if you need to. So flame test are one way, and you can take a little bit of the metal, perhaps put it on a stick, post it in the Bunsen burner, and see what colour that flame of the Bunsen burner goes. If it goes green, for example, you've got barium. If it goes red, you've got calcium. If it goes orange, you've got sodium. And if it goes lilac, you've got potassium. And crimson, you've got lithium. So making a list of those and putting those on your wall would be a really good idea. So that's one way then we can test for that first part of the metal. So for example, if we've got calcium carbonate, we might test this compound in the flame, and if it comes back red, we know we've got calcium first of all. But there's not flame tests for all the different types of metals, and another way that we can do tests for those positive ions is to add sodium hydroxide to the solution. And we remember this is a kind of flow chart of what happens. First of all, if you add sodium hydroxide and a dirty green precipitate is formed, that's iron 2. If a brown or orangey precipitate is formed, that is iron 3. And a light blue precipitate is copper. You don't need to remember about the light particularly, or the dirty. Just remember it's green is iron 2. Oh, sorry. Brown or orange is iron 3, and blue is copper. And then you can also have a white precipitate formed, which can be calcium, magnesium, or aluminium. Okay, so this brings us back to the periodic table, remembering that transition metals make coloured compounds. So we've got iron, iron 3, and copper making coloured compounds. Just remembering where this 2 and 3 come from. The ions in the transition metals can either have 2 or 3 ion electrons in their outer shell, so they can either make Fe2+, for example, or Fe3+ ions. So if you add sodium hydroxide and you get a colour change, that's great. You can stop there and you found out that that first part of your compound is iron 2, iron 3, or copper. So you might have something like copper carbonate, for example, but you don't know about this bit just yet. But you can tell if you get a blue precipitate that that first bit is copper. If you get white precipitate, it could be one of several things. It could be calcium, magnesium, or aluminium. Now, if you add excess sodium hydroxide, that means add loads more into the solution. If the white precipitate then disappears, you have yourself aluminium. So if you add more and it will dissolve, that is aluminium. On the other hand, if you add excess and it doesn't disappear, you've got two options. It could be calcium or magnesium. And at this point, you would do a flame test and work out that if the flame test went red, it would be calcium. If there's no real colour change, then it would be magnesium. So this kind of flow chart, I'd really recommend you just being able to write out over and over again. So have a practice on a blank piece of paper, writing it out over and over again for the test for metal ions, because it only came up a little bit last year, but I guarantee that it will be somewhere in your paper. So we've got the metal ions sorted now. We've worked out what the first part of our compound is. We can now look at the second part of the compound, and here comes some more very complex tests. So to test for that negative part, so it could be that we're looking at potassium sulfate, for example. We could be looking at potassium iodide, or we might have potassium carbonate. Okay, we don't know necessarily what this bit is. And we need to work that out now. So there's a few tests we can do. The first one is to test for halides. And from the periodic table, you remember these are group 7 ions, which the group 7 are called the halogens, but the ions of those are called halides. And to test for those, we add dilute nitric acid and silver nitrate. Nitric and nitrate stay together, so adding those two together. And the results of that reaction, if you get a white precipitate, that's a chloride. Green precipitate is a bromide. A yellow precipitate is an iodide. And that is how you work out those 3 halides. And those are the only 3 that you need to remember. So again, perhaps having a little way to link the 2, W and C and B, and Y and I. So thinking of a couple of words that will help you link those 2 things together. It might be a footballer that you know with those 2 letters. It might be a friend that you know with those 2, or 2 different people that you can kind of imagine together in a scenario to try and remember those ones. That's the halides then. That's how we'd recognise the halides. We've got the sulfates then. So if you had something like calcium sulfate or magnesium sulfate, to know that it's a sulfate, you add dilute hydrochloric acid and barium chloride. So this is the extra couple of things that we add to test whether it's a sulfate. And if a white precipitate forms, that means you have a sulfate. Because you have the barium ions from the barium chloride reacting with the sulfate and making barium sulfate. Now, you've done this before in a precipitation reaction in C2 topic, and you might recognise that barium sulfate as that white powder. So it's because the barium ions in there reacting with sulfate to make that white powder. And I should have said up here that it's the silver ions in that nitrate reacting with your halide to make that solid. So it would be silver iodide, for example, or silver bromide, or silver chloride. The last test that we can do then should be the easiest one for you, because you've done it so much throughout your school lives, and that is the test for carbonates. And to test for carbonates, you add acid and CO2 is produced, which makes lime water go cloudy. So if we were just to put a couple of these together, for example, if we were testing for calcium carbonate, we perhaps would do a flame test for the calcium and find that was red. And we'd add a little bit of acid and see lime water go cloudy, and to find out that that was the carbonate bit. Another example, if you had copper sulfate, for example, CuSO4, for this bit you'd add sodium hydroxide from a few slides ago, and that would produce a blue precipitate. And for the sulfate, you'd add dilute hydrochloric acid and barium chloride, and a white precipitate is formed. So this is the kind of idea. You need to identify a compound, and you look to test for the positive ion part of it, and then the negative ion part of it. So unfortunately, really sad face, you do need to know these tests for the exams. So please write them out again and again and again until you've committed them into memory. So just to complete this session then, I've got a couple of questions for you on these testing for positive and negative ions. I'm just going to give you a couple of minutes to go through those, just 3 questions, and then I'll come back and see if you've got them correct. Feel free to post any last messages on Frog before I head off tonight as well. Don't forget, you won't get given these tests in the exam. Unfortunately, you will have to remember them. Okay, just one more minute and then we'll go through and then we'll bring this tutorial to a close. Okay, let's go through the answers then. The first one's what colour is produced by barium compounds in a flame test? Barium is green. The next one, chemical tests are carried out on the following substances: sodium iodide, aluminium sulfate and copper carbonate. Write the name of the substances identified by the following tests. Well, if hydrochloric acid isn't gas produced, that must be talking about the carbonate. So this one would be copper carbonate. Doesn't prove to us that it's copper, but out of those three options, it must be the carbonate. Sodium hydroxide is added and a white precipitate is formed. So in this case, it must be the aluminium sulfate. Again, it doesn't tell us that it's definitely a sulfate, but out of these three options, it must be this compound. And finally, a flame test produced a yellow-orange flame. That must be from the sodium, so this compound must be sodium iodide. And this is a bit more complex question. It says, describe the tests you would do to prove a substance was magnesium bromide. Well, first of all, you have to prove the magnesium bit and the bromide bit. So talk about the positive ion first of all. It's worth 4 marks. So first of all, for the positive ion, you need to add sodium hydroxide. And you would get a white precipitate. Precipitate just means the solid that's formed, okay? So white precipitate, because it's a precipitation reaction. You would then add excess sodium hydroxide. And then if it disappeared, it would be aluminium. But if it stayed, you would know it was calcium or magnesium. So then you'd need to do a flame test to make sure. So then you would do a flame test. And if no red was seen, it proves it's magnesium. So long-winded way there to get to magnesium. If I add sodium hydroxide, add more, and if it still doesn't go away, do a flame test and check that there's no red. So that's for the positive ion. And then for the negative ion, for the bromide part, we'd need to add dilute nitric acid and silver nitrate. And if a cream precipitate formed, that would prove that we have a bromide, and that would prove that we had magnesium bromide. So those are the type of questions that it will ask you about those tests for positive and negative ions. Feel free to come and ask us for lots more example questions that we can give you to help you practice with those. So very well done for taking the time to do loads of excellent revision. Thank you very much for joining me this evening, and feel free to post any further questions that you've got on the FOG page.